Okay, section 7.3, if we look at example 6, it's about figuring out a cumulative resistance of a bunch of resistors in parallel in a DC circuit, okay, direct current circuit. The formula is not explicitly shown here, but what the formula is for finding a total resistance, it's a reciprocal. 1 over the total resistance equals 1 over the individual resistance, and then I add them all up, again, in parallel. Okay, if you ever take any kind of class on circuits or anything like that, you will no doubt study this, okay? So if you look at the example, find the total resistance in a parallel DC circuit with 3 branches, each rated at 4 ohms. That little Greek letter omega is pronounced, it stands for an ohm of resistance. It's a unit of electrical resistance, okay? So I've got a 4 ohm, a 10 ohm, and a 20 ohm circuit in parallel with one another. I want to find the total resistance, okay? And the formula is 1 over, okay? So we're going to have a weird looking denominator here. Really strange, common denominator, I mean. So 1 over R, and again that would be our total resistance, equals 1 over the individual resistance, and then I add them all together. So I've got 4 ohms plus 1 over 10 ohms plus 1 over 20 ohms, right? It's an equation. Find R. I've got a bunch of denominators at work here. It's a fractional equation. Okay, so we need to find the common denominator, and then we're going to clear those fractions out of there, just like we did prior in previous examples. Well, if we just look at the numbers, the 4, the 10, and the 20, I hope the common denominator is obvious. It's a 20, right? But we must also consider that letter R. That's part of the denominator. So my common denominator is really 20R. Because if I could get a 20R here, a 20R there, a 20R there, and a 20R there, they would all be the same denominator. And I could do that. I could get a 20R everywhere in that denominator by multiplying appropriately through all these fractions. Okay, we don't actually do that, though, with a fractional equation. If the task was to just add all 4 of these together, for example, then we would have to do that. We would have to get a common denominator of 20R everywhere and then add them together. But with a fractional equation, we don't have to do that. We can clear those fractions out of there. Okay, so I need to multiply numerators only by 20R. So think of it as 20R over 1. And what's going to happen? I'm going to get a 20R over R for this piece over here. I'm going to get a 20R over 4 plus 20R over 10 plus 20R over 20. Alright? Now look what happens. Pardon me, I'm going to grab a marker. Look what happens. I'm going to cancel away all of those fractions. They all go away, don't they? Those fractions all disappear. The R's cancel here, and I'm just left with a 20. The 20 and the 4 divide away into a 5, so I'm left with 5R. The 10 and the 20 divide away into a 2, so I'm left with 2R. And the 20 and the 20 divide away into a 1, so I'm just left with an R. Okay, so now I've got a very manageable equation here. 20 equals, I'll combine all these like terms, 5, 6, 7, I've got 8R. How do I solve that? I divide by 8 on both sides. I'm going to have the fraction 20 over 8 equals R. Okay, which I would then reduce. I could, there's techniques to reduce, of course. The quickie is just cut it in half and see what that does for you. So 10 over 4, but I could do that same thing again and give me a 5 over 2. Okay, so my resistance for this circuit is 5 halves, okay, which I could, of course, also turn into a decimal if I chose 2.5. Okay, so that is a nice little example on how we can apply these fractional techniques here. Okay, and that was example 6 on page 340. All right, so we could call it 2.5, again, that unit is the Greek letter omega, pronounced ohm, 2.5 ohms. All right, awesome. Let's look at our next example. Our next example involves a rate of work. Whenever you hear that word rate, it's a fraction, okay? Speed is a rate, right? Usually measured in miles per hour. It's a fraction. The cost of hamburger at the store, right? Well, it's usually dollars per pound. It's a rate. It's a fraction. You hear that word per, it's a fraction. Okay, so if I'm assembling something on an assembly line, I can assemble so many products per minute, per hour, per day, per something. That's a rate. Okay, a rate always has that kind of fraction attached to it. So if I wanted to know how many items I could assemble, or if we stick with the speed example for a minute, if I'm going 50 miles per hour, and then I'm traveling for 3 hours, we all know if I multiply by 3 hours, hours cancel, and I've traveled 150 miles. Okay, so the formula, when you're talking, this formula here would be distance equals your rate times your time. 50 miles per hour is the rate. I traveled that speed for 3 hours. My distance is 150 miles. Same idea for some kind of amount of work we want to do. And if you turn your attention to page 341, right here, the amount of work equals a rate times a time. It's the exact same formula as that distance formula. Distance equals rate times time. The amount of work we do equals the rate times time. Now the rate in this case will be some task we are accomplishing, and it takes us so long to accomplish it. And then if we repeat that process over and over and over and over again for some length of time, we can figure out how many of those processes we can complete. So if you look at example 7 here, a carpenter can install 1 door in 3 hours. Find the number of doors the carpenter can install in 8 hours. Okay, so my rate is going to be 1 door per 3 hours. It's a fraction. My time is going to be 40 hours, and then I can figure out the W, the work, how much work I'm accomplishing. So let's do that. My work, W, equals my rate times my time. Okay, and depending on the situation, W will stand for all kinds of different things. In this case, W stands for how many doors can my carpenter install here. Okay, I don't know. Let's figure it out. We know we can do 1 door, and I'm going to go ahead and write it out. 1 door per, what did it say here? 3 hours. Okay, again, sometimes I use HR for hours. Sometimes I'll just use H. My apologies for not being consistent. Our book is using H for hours here, so I'm going to try to remember to do that the rest of the time. You see up there I used HR. I'm just so used to doing that. So 3 doors per 1 door in 3 hours, but I'm going to work a 40-hour week here. So times 40 hours. Okay, slap a denominator of 1 under it if it makes us feel good. What's going to happen to my units? Goodbye hours, goodbye hours. I'm only going to have doors left, and that's what I want. How many doors can I accomplish here in a 40-hour week? Well, it's going to be 40 divided by 3. The unit would be doors. Okay? What is 40 divided by 3? Well, maybe it doesn't work out to be a perfectly nice answer. In this case, it doesn't, right? 40 divided by 3, if I perform the division or perform the decimal, what are we going to get here? Let's do 40 divided by 3. Let's turn it into a mixed number. Goes in there 1 time, subtract, and I get a 1. Bring down the 10, 9, 1. So I can do 13 1/3 doors. Okay, so basically 13 doors in a 40-hour work week, a little bit more than that. Okay, put it in practical terms, we'd probably say 13 doors, right? We'd round down a little bit and say, I can do 13 doors in a week. I don't know what that means. The whole frame, cutting the opening, I don't know what it means to do a door. Okay, we'd have to identify exactly what that means to do a door, but we can do 13 of them in a week's time. Okay, 40 hours. Okay, there we go. If you look at 342, kind of the middle of the page, now we're going to have different individuals contributing towards a common goal, and those people have different rates of production. Okay, so it gets a little more tricky here. We've got maybe two people or more than two people working to achieve a common goal, and they're not working at the same speed. Okay, let me pull the book up. I think it'll be helpful. If we look here at this example, at this green box here. Formula for completing one job, so we're doing one task, but we've got two people, person A and person B, working together. Okay, well, we're just going to have two separate little problems here that we're going to add together, because how much work the first person's going to do is going to be added to how much work the second person does, and together they're going to complete this job. Alright, so for person A, there's a certain rate of work associated with person A, and a certain length of time that person A is working. For person B, there's a rate of work associated with that person and the amount of time that person is working. With this formula, they wouldn't necessarily have to work the exact same amount of time. We'll see how the examples go here, but chances are they're going to work together the same amount of time. They're just not working at the same speed. One person's working faster than the other, but altogether they're going to get the job done. So let's check out example 8 here. While we don't have people, we have two different water pipes trying to fill up a tank. Okay, pipe 1 fills a tank in 6 minutes, and pipe 2 fills the same tank in 8 minutes. Okay, so pipe 1 is going faster. It's pumping more water than pipe 2, because if pipe 1 were working all alone, it could fill the tank in 6 minutes. But if pipe 2 were working all alone, it would take longer. It would take 8 minutes. Okay, so now let's turn them both on together with an empty tank, and let's see how long it's going to take to get it done. Alright, that's the question. Always ask yourself, what's the question? What am I trying to find here? How long does it take for both pipes to fill the tank together? Okay? So they're working the same amount of time. Okay, if we say we're going to shut off one pipe, after 5 minutes or something, now that becomes a different animal, more complicated. They're both going to work together the full time until the tank is full. All right, so we've got pipe A here is pumping at, it takes, pipe 1 fills the tank in 6 minutes. Okay, so what's our rate? 1 tank per 6 minutes. Okay, usually in a rate situation, the time is almost always on the bottom. Tanks per minute, miles per hour. Okay, time is usually on the bottom in a rate problem like this. So pipe A can fill the 1 tank in 6 minutes, and I'm going to turn pipe A on, right, for a certain amount of time, but I don't know how much time I'm going to turn it on. So I have to figure it out. I'm just going to call it T minutes. Okay. If pipe A were working all by itself and I left T be 6, then 6 minutes cancels 6 minutes, and I've got 1 full tank there. Okay, so that makes sense. That's the first pipe. But I've got a second pipe helping out here. That second pipe can fill the same tank in 8 minutes. So I can fill 1 tank in 8 minutes. And how long am I going to run this pipe? Well, the same unknown number of T minutes. Okay, so 1 tank in 6 minutes, 1 tank in 8 minutes. I'm going to add them together with the same amount of time, and what's my end result here? I want to fill 1 tank. So there's my equation. Okay, if I go ahead and cancel out units here, and I'm going to drop units here for the time being, I'll have 1/6 times T, again the minutes cancel, the only unit left on the board is tank. Tank plus tank equals tank, so that makes sense. 1/6 T plus 1/8 T equals, what's that going to be? 1, right? 1 tank. I'm dropping the name tank for a minute here. Okay, 1/6 T plus 1/8 T equals 1. What T is going to accomplish this? I don't know. I've got to solve this equation. It's a fractional equation. I've got different denominators at work here. If I find the common denominator, I can clear those fractions right out of there. So I have to find the common denominator of a 6 and an 8. Okay, remember we talked about different ways to find common denominators. One way was we could factor each one, but if the numbers are small enough, I said, hey, just count off to the side here. 6, 12, 18, 24, 30, 36. Start counting by sixes, then start counting by eights. And the first time you hit a match, we hit a match at 24. That's my smallest common denominator. Okay, so I'm going to multiply through numerator only by that number, which will be 24 over 1 if I think of it as a fraction. So it's 24 over 6t plus 24 over 8t equals, that'll just be 24 there. These fractions now divide away nicely. 4t plus 3t equals 24. Add those t's together, I'm going to get 7t equals 24. Divide by 7, divide by 7. T equals 24 over 7 minutes, right? T is in minutes. Well, what is that? That's kind of a goofy number. Let's turn that into a mixed number. Well, I know 7 times 3 is 21. I'll have 3 left over, so 3 and 3/7 minutes. With both pipes operating together, it only takes 3 and 3/7 minutes to get it full. Now, always give it the stupid test. Does that make any common sense to what I know? I know that one pipe alone can do it in 6 minutes. I know the other pipe alone can do it in 8 minutes. So working together, they better be able to improve the 6 and the 8, right? They have to be less, and they are less. So that at least passes the common sense test, okay? Always check for that. Okay, I'm going to pause it here, I think. There's a couple more examples we will pick up on the next video.